Hi, and welcome to our discussion on atmospheric dynamics. We're working our way through mass continuity. This is the second video on the mass continuity equation. And we left off with our last video looking at the mass continuity equation in its various forms. You can either do it in Cartesian coordinates or pressure coordinates. With the Cartesian coordinates, of course, you're dealing with the x, y, and z axes. And your components of wind are U, V, and W. And we can put that in a lot of different forms. We could put it in the shorthand delta, Greek letter delta for divergence, or we could use vector notation del dot V, or we can actually just spell out the components. But meteorologists work more in pressure coordinates. As you guys know, most of you know that we use constant pressure charts. So pressure is the meteorologist's friend. It's the vertical component that we use. And you know that as you go up through the atmosphere, pressure decreases. So it's opposite of altitude. As you go up, altitude increases, but pressure decreases. So that throws a little curveball in our formulation. But regardless, this is what the equation of mass continuity looks like in pressure coordinates. Omega is your vertical velocity. It's the change in pressure with time. And then using pressure coordinates, we've got instead of the dz, we've got dp in the bottom. And we'll look at this and we'll explain how this works. So overall, what you need to know is that the mass continuity equation tells us that if there is convergence or divergence in the atmosphere, it will cause either rising motions or sinking motions, depending upon the distribution of convergence and divergence throughout the atmosphere. So we're going to start out with the equation of mass continuity in pressure coordinates, and that's d omega dp is equal to the convergence or divergence in the atmosphere. So we're going to break this equation apart and look at each section of the equation and each term of the equation. So the first term we're going to look at is the omega term. So we separate the derivative here. We bring the dp on the other side, as you can see. And also we move the minus sign around, and you can do that just multiplying both sides of the equation by -1. So let's take a look at this first term, the d omega, which is your vertical velocity. So our first term is d omega, and omega is our vertical velocity. So this would be a change in vertical velocity, where omega means dp dt. That means a change in pressure with time. So how does that relate to vertical velocities? Well, in our atmosphere, pressure decreases as you go up. So a rising vertical motion in the atmosphere would mean that omega is negative, because as you go up through the atmosphere, pressure decreases with height. So over time, as the air rises, pressure is decreasing for rising motions. Conversely, if the air is sinking in the atmosphere, as it gets closer to the ground, over time, that means pressure is increasing. So a sinking motion means that pressure is increasing with time, which means that omega is positive. Okay, so we looked at the first term, which was your d omega term, the change in omega. Now let's take a look at the second term on the other side of the equation. And this term, of course, we said was your divergence term, which tells us about the convergence and divergence in the atmosphere. So if there is divergence in the atmosphere, then del dot V, or divergence, is positive. It's greater than 0. However, if del dot V is less than 0, that means we have convergence in the atmosphere. So by definition, convergence is negative. So what we're going to do now is we're going to evaluate each term. We kind of describe what each term is, what it means. Now we're going to look at how it changes in the atmosphere. To do that, we're going to look at the first term. We're going to look at the derivative of omega, the negative derivative of omega. And as you remember, omega is vertical velocity. So what the derivative of omega means, it means the change in the vertical velocity. Now we're doing this with respect to the layer of the atmosphere. In other words, over a certain change in pressure, dP, which you see on the right-hand side. So what that means is we're going to compare the vertical velocities in the upper atmosphere with the vertical velocities in the lower atmosphere. So that's what we'll do. We'll separate our derivative. We'll say that the derivative of omega, minus the derivative of omega, I should say, is equal to minus omega upper minus omega lower. So we're looking at the upper level vertical velocities and the lower level vertical velocities. Now we'll take a look at the other side of the equation, and this is the side with the convergence and divergence. And what the dP means here with the del dot V, it means that once again we're looking at the upper and lower levels of the atmosphere and comparing the convergence and divergence in the upper and lower parts of the atmosphere. So we'll break that out, we'll separate that and say that that side of the equation, the right side of the equation, basically is just the upper level convergence or divergence minus the lower level convergence and divergence. Oh, this gives me a headache. Too many dot products, too many omegas, too many derivatives. But simplified, what this says is that the vertical velocities in the upper atmosphere are a result of the difference in convergence and divergence throughout the depth of the atmosphere. And you probably knew that already. You learned this back in your basic meteorology class, your introductory meteorology class, that if there's upper level divergence and lower level convergence, that causes rising motions. Well, we're doing it mathematically now. So if you have low level convergence, that means that your divergence term is negative. It's less than 0. And if you have upper level divergence, it means, of course, the divergence term is positive in the upper levels. So if we stick that into our mass continuity equation, the one that we simplified, that means that for the upper level divergence term, that's positive. The lower level divergence term is negative. A negative minus a negative is a positive. So the right-hand side of that equation is positive. To make the left-hand side of the equation positive, in other words, to make that minus omega u term positive, that means that omega needs to be negative. And a negative omega is rising motion. Conversely, if you have lower level divergence and upper level convergence, that results in sinking motions. So lower level divergence means that the divergence term is positive or greater than 0, and upper level convergence means that the divergence term is less than 0 or negative. So let's stick those into the equation. Here we go. We've got upper level convergence, it's negative. Lower level divergence, it's positive. So let's see, upper level convergence is negative, so that's a negative minus a positive. So on the whole right hand side would be a negative minus a positive would make that negative, right? So the whole right side is negative, and to make the left hand term negative, the omega term, we have a minus omega. To make that negative, that means that omega needs to be positive. And in a positive omega is sinking motion. So this is really kind of complex, but the concepts are so simple, but mathematically we've got to prove this. So I hope you are reaching for Excedrin or for Advil or something right now, because this gives me a headache, but this is how the atmosphere works. And we'll wrap up with one more video in the mass continuity equation, so look forward to that.